In this pre-lecture video, I want to address another calculus technique. We talked about derivatives and got some refresher there when we were working with the Taylor series. Now let's talk about integrals. By now you've taken many calculus classes and you've probably learned a lot about integrals. So I'm not planning to teach you that stuff again. I'm relying on your previous knowledge from all those calc classes to do integrals. So I'm hoping that you know how to do integrals like the ones that are shown here. And even if you don't know right away how to do it, I hope you know how to approach the problem. For example, this one here is a U substitution. This one here is by parts. And that trig function down at the bottom it needs a trig identity. U substitution and integration by parts are the ones that are most important in physics. So if you don't remember anything about those, I would ask you to go back and review your calculus notes. Now is a great time to do that, to review how to do integration by parts and how to do U substitution. So those are the things that we will use most often. But I'm not going to go over those things again. Instead, what I want to do today is to give you a sense of some additional steps that physicists do when they're attacking an integral. So I want to teach you some tips and tricks in the way that a physicist looks at an integral. And you probably didn't learn these things in math class because physicists have additional tools at our disposal that math doesn't have. So that's what I want to get started with right now. So let's call this a set of 4 additional steps to working with integrals in physics. Okay. So the first one is pretty straightforward. It's just identify the integration variable. In math classes, you don't have to do this because they're nice and they always give you an integral where the integration variable is x. Like this one up here, the integral always has dx at the end of it because x is the variable that you're integrating. But in physics, it's not so simple, right? There's many quantities in the real world, and we have to do integrals of many of these quantities. So for example, here's an integral that comes from thermal physics. I'm just going to write it down so you can know that this integral is relevant to the real world. And like most things in the real world, it's a little complicated. So there it is. There's an integral. It's got a bunch of different variables in it. And this comes from thermal physics. And if you didn't see this before, rather than freaking out about it, the first thing you should do is think about, okay, what is the variable that I'm integrating here? And it's the thing after the d, right? So in this case, the thing after the d is nu. It's the Greek letter nu. So this is my integration variable. Okay. Of course, all of the ones that you encountered in your calc class have dx, so x is the integration variable. Here it's this Greek letter nu. And that means that everything else can be treated as a constant. And so all constants can be brought outside of the integral, right? It's obvious if it's numbers, but here it's not numbers, it's other variables. Okay, so what can I bring outside? 8 pi is obviously I can bring outside. H I can bring outside. C cubed I can bring outside. So I can bring outside 8 pi h over c cubed. And then inside I'm going to have nu cubed and then 1 over e to the h nu over kt minus 1 d nu, like this. Okay. So I can bring those things out because they don't depend on the integration variable. I cannot bring anything which has nu in it outside of the integral. I cannot bring this outside because it depends on the integration variable. I can only bring constants which don't depend on the integration variable outside. This is a common mistake that I notice. So a lot of times students will bring like this whole thing outside, but you can't do that. If it depends on this integration variable, it has to stay inside the integral. If it doesn't depend on the integration variable, you can bring it outside. Yeah. Now the second step is to think about the units. What is the units of the result? This is something you never do in math class, right? They never explain what dx means. They just they say, well, dx is some notation denoting an integral. But in physics, it has a meaning, okay? And the dx has units, okay? And in physics, dx means a small amount of x. So for example, let's say x is a length. Let's say if x is a length, then dx is a small length, right? And if, for example, if t is a time, then dt is a small time. And that means that when you're thinking about the units of this integral, you have to include the units of the dx, or the dt, or the d nu, right? So very important is that the units of dx are units of length, right? Assuming x is a length. The units of dt are time. Okay? So when you're analyzing the units of an integral, you need to include the units of this d, whatever the integration variable is. Here's an example. Let's suppose I've got some integral I is equal integral, let's say 0 to 1, t squared x dx, let's say. What are the units of the result? T is a time, x is a distance. Okay, first of all, this thing, the integral sign, remember, that's basically just like adding up a bunch of really tiny things. So that doesn't add any units. But these things in here have units. Okay? So let's do some unit analysis. The units of I are going to be equal to the units of t squared times the units of x times the units of dx. Remember, very important, you got to include this, right? That has units. And the units of dx are the same as the units of x. Okay, so this would be seconds squared. This would be meters, and this would be meters, right? The dx has units of meters. So my answer here would be the units of I would be equal meters squared times seconds squared. Okay. This is something you can use to check your result. Third thing, think about what the result can depend on. When you've got multiple variables showing up, it's helpful to think about what are the variables that are going to show up in my answer for this integral. So let's say we've got this integral, let's call it I, is equal to integral a to b, some function of x and y, and then let's say the integration variable here will be dx. You'll notice that in physics we generally do definite integrals. We have the limits here on the integral. So we almost always are doing definite integrals, so we're plugging in the limits at the end. Okay, what does this depend on? Like, what will the result depend on? I is going to be a function of what? That's the question. Here's the thing. It will not depend on x. It will depend on b and a and y. But I will not depend on x. Why not? Because when I have a definite integral, first I take the integral, and then everywhere I plug in where I have x, I put in b, and then I subtract everywhere I have x, I put in a. So the x disappears from my answer when I have a definite integral. So you can think about this definite integral as some kind of operation which gets rid of the integration variable. So definite integrals get rid of the integrational variable. As an example, let's say I go back up here, I equals, to this example I had before, I equals 0 to 1 t squared x dx. Well, before I do it, what variable can it depend on? It will not depend on the integration variable x. That will be gotten rid of when I plug the limits in. So I know at the end of the day, I'm going to have something which depends only on t. I will be a function of t only. Okay. So let's actually do it. What do we get? The t is not the integration variable, so it comes outside. Integral 0 to 1 x dx. And this integral is straightforward to do. T squared over 2 x squared evaluated at 0 and 1. So I get t squared over 2 times 1 squared minus t squared over 2 times 0 squared. This whole thing is 0. I get t squared over 2. And that depends on t, right? It doesn't depend on x, because x disappeared when I plugged in the limits. Let me make a related point. The integration variable is called a dummy variable. It doesn't matter what I call it. Let me give you a simple example. Same one. Let's do 0 to 1 t squared y dy. See, what I did is that's the same as up here, but I changed the name of the integration variable from x to y. What is this integral? I would do all the same steps, right? T is not the integration variable. It comes outside. 0 to 1 y dy. And then the integral of y is 1/2 y squared, evaluated at y equals to 0 and 1. And I get the same thing, t squared over 2, right? So it doesn't matter what I call the integration variable. I can change the name to anything I want. So integration variables can be renamed at will. Basically, anytime you want to, you can rename it to something else. I could do the same thing. Integral 0 to 1 t squared. Maybe I call it q, right? q dq. That's still going to be t squared over 2. Doesn't matter what that variable is, because the result doesn't depend on that variable, so I can call it anything I want. Once you've thought about all of these things, you've thought about the variables that are showing up in the integral, you've thought about the units, I'm going to ask you to use a u substitution to change the variable to a dimensionless variable. Dimensionless integration variable. When I say dimensionless, I mean unitless. Right? I want to change the integration variable to a variable that has no units. And when you do this, your integral will take the form of like this. It'll have some dimensionful constants So those are the things that have units, which will be outside of the integral. And then it will be multiplied by a dimensionless integral. Which is just a bunch of, which is just a number, right? So it has no units. This is just a number. And this is all of the physics, right? Physics, we deal with quantities that have units. So in a sense, when you do this, you're factorizing the physics from the math. I'm getting all the physics out in front, and then I'm left with an integral that looks similar to the integrals I had in calculus class. It's just I have to calculate the number. How do you find a dimensionless variable? I need a variable that has no units. So how to find a dimensionless variable? There's a couple tricks. The first one is that if you have two things that are added together in your integral, like, so for example, x squared plus y squared, if that shows up in your integral, two things, you can't add them together unless they have the same units. So that means x and y have to have the same units. And that means that x over y has no units. So that's a good dimensionless variable. The other trick is to look for things inside of sine or cosine or exponentials. So if your integral has like e to something, or sine of something, or cosine of something, the arguments of those are always unitless. So whatever goes here is always unitless. So if I look at what's inside of my exponential, or inside of my cosine, or inside of my sine, that already tells me something which is going to have no units. So this is a good dimensionless variable. So those are the 4 tips that I would like you to try to do every time you encounter an integral. I'm going to illustrate all these with an example. And this is an example which came from an old exam. So you may encounter the integral I shown at the right in a quantum mechanics class, where r is a distance. Few questions. What variables will the integral I depend on? What are the units of the integral I? And then defining a suitable dimensionless variable, write I in the form of some dimensionful constants times a dimensionless integral. So first step is to identify the integration variable, r, right? And this is a definite integral. It goes from 0 to infinity. So that means that at the end of the day, my result cannot depend on r, okay? So for part A, r is the integration variable. The result cannot depend on r. The only other variable in this expression is a. So I will be a function of a only. Okay. All right, now part B. What are the units? Okay, so the units of I, what do I have here? I've got the integral sign, which doesn't add anything to the units. I've got 4, which has no units. And I've got r to the 4 on the top. And then I've got a to the 3 on the bottom. And then I've got dr here, right? I have to include the units of dr. Dr means a small distance, so it has units of distance. Why didn't I include the e? Because e to something is always unitless. So this whole thing is unitless. Okay. So what are the units of I? It's going to be the units of r to the 5th divided by a cubed. Now the problem is, what are the units of a? In the first sense, it seems like you don't know what the units of a are. But remember, whatever's up in the exponent, in this case r over a, has to be unitless. Okay, remember that e to something, whatever goes here is unitless. So that means r over a is unitless. So that means r has the same units as a. So the units of r are the same as the units of a because the exponent has no units. So the answer will be r to the 5th over a cubed, so that'll be r squared. So the units will be in meters squared. So that's the answer. We'll definitely have units of meters squared. Now let's do part C. Let's try to define a dimensionless variable. So here we go. Let me write down the integral one more time. Okay, so let's go through the steps again. R is the integration variable, so I can only bring constants outside which don't depend on R. So the 4 is obviously a constant. And the a cubed doesn't depend on r, so a cubed is a constant. And those are the only things I can bring outside. I'm left with this. Right? R to the 4, e to the minus r over a, dr. Okay. Right now the integration variable r is a distance. It has units. But I want to define a dimensionless integration variable. That's what I'm trying to do, right? I want to change to a variable which has no units. So what is a quantity which has no units here? I can see up in the exponent, right, r over a. I know that a has to have the same units as r. So an obvious choice, dimensionless combination is r divided by a. Right? I know that r and a have the same units because they're in the exponent together. And that means that r over a has no units. So let me make that my dimensionless variable. Let me call it u. So we'll say u is going to be equal to r over a. And du is going to be equal to dr over a. And let's substitute in, do the u substitution. So I is going to be equal to 4 over a cubed. Now I got to change the limits. Whenever I make a u substitution in a definite integral, I have to be careful about the limits. In this case, when r is 0, u is 0. So the lower limit is 0. And when r is infinity, u is infinity. So the limits actually stay the same in this case, but that's not always true. You have to be careful about what are the limits going to be when I change to my new variable. Okay, now r to the 4th is going to be u times a to the 4th. E to the minus u, and dr is a times du. Okay. Let's count everything up. Now the new integration variable is u, so everything that doesn't depend on u comes out front. 4 over a cubed. How many a's do I have? I've got 4 here, and then another one here, so that's a to the 5th coming out front. 0 to infinity. I've got a u to the 4, e to the minus u, du. Let me simplify it a little bit. I is equal to 4, a squared, integral 0 to infinity, u to the 4, e to the minus u, du. Okay. Now we said, going back up to part B, the units of I are in meters squared, and the units of A are meters. So that means that this here is all my, this has units of meters squared. This has no units. So this is just some number. Okay. Now, to calculate what the number is, you got to do calculus. You have to do, actually this is a pretty bad one to worry about. So u to the fourth e to the minus u, you'd have to do integration by parts a whole bunch of times. But whatever it is, it's some number. And so I know for sure that when I go through my calculus techniques of evaluating this integral, my I, remember it depends only on a, is going to be equal to 4a squared times whatever that number is. It's just a number. So all my physics is here. And then I got to do math to figure out what this number is. By the way, because I know it's burning in your mind, you want to know what that number is. When you do this integral, this number actually turns out to be 24 by doing the integral. Okay, but even before you do that integral, you have an idea of what the answer looks like, and you just have to calculate what is that number. Let me try to summarize. So these are the steps that I would like you to go through when you encounter an integral. You know, think about what can the result depend on, think about what are the units, and then think about changing to a dimensionless integration variable that'll help you separate the physics from the math. We'll do some additional examples of this in class, so I will see you all then, and bye for now.